Thank you so much for coming. My name is Josh Gordon. I work in developer relations, and you may remember me from such shows as AdWords API support, and later Android Auto and Android TV education, and now machine learning education. So today I want to talk to you about TensorFlow, and specifically I want to focus on how TensorFlow can really enable something called machine learning for everyone. And basically I'd like to dispel the notion that to use machine learning, to understand machine learning, and to benefit, you need a bunch of PhDs and an army of mathematicians. So first of all, thank you so much for coming. I've worked a lot with the NYC GDG, and it's always been a pleasure. So I'm continually impressed by you guys, and I spend a lot of time in cubicles working on decks and stuff, and it's such a pleasure to get out and interact with developers. So it means a lot to me, so I sincerely appreciate it. So real quick, what TensorFlow is, and then I'm going to spend the majority of the talk giving you some background on machine learning, because I want to make sure everyone's on the same page. So briefly, TensorFlow is an open source machine learning library. It powers almost everything at Google, from things as mundane as a spam filter in Gmail to something as magical as AlphaGo. Recently it was open sourced, and the decision to open source it, I believe, was made by Jeff Dean, and the idea was that we really want to enable and empower researchers in the community to benefit from some of the software engineering that's taking place at Google, so they can focus on their research and not writing highly optimized code. That's a lot to digest all at once, so we'll get there. And I want to start by talking about the difference between apples and oranges, which I like to use to introduce machine learning. Then I'll give you a quick demo of TensorFlow, and finally we'll write Hello World. All right, so now I can actually get into the talk. So who is familiar with machine learning? Who's heard of machine learning? Okay, that's outstanding. So what's absolutely interesting is 5 years ago that wouldn't have been the case. So who has written a machine learning program? It can be anything from Hello World to spam filter. Okay, so that's still outstanding. So I'd say that's about 30%. That's excellent. For folks that are brand new to it, and folks that might have heard of it but aren't super sure what it is, I'd like to do a quick introduction. So I want to talk about solving a problem that's absolutely impossible to solve without machine learning. And this is true no matter how good of a developer you are. It's totally impossible. And it's, can you write code to tell the difference between an apple and an orange? And so the idea is the input to your program is going to be an image file. And you can write some Python or Java, you can write some rules, and you can analyze it in whatever way you want. And your job is to output, it's an apple or it's an orange. Who can give me a real quick idea how they might solve this? Let's pretend you were like in a college class and your professor gives you a homework assignment and says, all right, I need you to write a program to do this. Like, what's one simple idea? What's one strategy you could use? Yeah,
Color.
Just shout it out.
Color.
You got it. So count the colors. So typically apples are more red. And so that's exactly what I would do to start. So I'd start writing a program and call it classify. I'd input like an array of pixels. And then exactly like you guys said, I would try and count the colors. I'd compare orange versus red pixels, and if there's more red, I'd output apple. So what can go wrong with that? Yeah, a green apple. That's a great example. Something else that could go wrong is a black and white photo. Okay, crap. So your professor gives you a black and white photo and says, all right, now what? So now what can we do? Shape. Okay, shape is awesome. So I use the word texture instead of shape. Like oranges tend to be a little bit bumpy, so maybe I could, write some insanely complicated code in Python to try and detect texture, and if there's more bumps than not bumps, I output orange. Then your professor says, all right, great, like congratulations, that took you a week, you're gonna get that A, but now I want you to work with pears. By the way, pears are smooth and they're green, just like your apples, right? So it goes on and on and on, so now you write code to handle pears, and then your professor says, all right, we got some grapes, so you write some more code, right? And it goes on and on and on and on. And the problem is, every time he or she gives you a new problem, you have to start all over again. So all that Python you've written is just totally useless. And this is not a scalable solution to solve this problem. And apples and oranges are quite simple. Like, what if you wanted to write code to recognize a cat, right? There's millions of things, millions of types of objects in the world you might want to recognize. And it's doing this by hand is impossible. And the reason is because data is incredibly high dimensional, and it's very noisy. So when we look at a cat, our brains are unbelievably good at this problem. I have absolutely no idea how they work. Maybe somebody in neuroscience does, but it's extraordinary, right? It's so easy for us to say that's a cat. But under the hood, let's pretend this image is only 100 by 100 pixels, and it's black and white. It's a really tall, a small grainy image, right? But even 100 by 100 pixels, that gives you 10,000 different pixel values, right? Just for black and white. So the data is incredibly high dimensional, and it's almost impossible to write code to process that data in a way that makes sense to us. And we see this with problems, tons of actually interesting problems that we're really interested in solving. So this is vision, and vision is great for a quick example because it's easy to understand. Other problems that for whatever reason seem to be less interesting to people are voice recognition. So I worked for many years on voice recognition, and it's such a critical problem. I was really interested in trying to build systems that could understand the elderly a little bit better, since their speech tends to be a little bit slower and a little bit broken. And it's incredibly hard to develop an accurate voice recognizer. In the last several years, though, that's totally changed. So if you use speech recognition on Android, all of a sudden it got extraordinarily good. And there's two reasons for that. Voice recognition and image recognition have always used machine learning. But recently, there's a new field of machine learning called deep learning, which is what TensorFlow is specifically good for, and I'll get into that in a little bit. There's many definitions of machine learning. A very simple one is it's the study of algorithms that learn from experience and examples instead of relying on lots of hard-coded rules. So to train an apple or orange classifier, you wouldn't write lots of Python. Instead, you'd write a program that basically could use statistics to learn from examples. So at a high level, you would basically feed it lots of examples of an apple and lots of examples of an orange. And you would write a program that can find just correlations in the data. And it can use those correlations to predict the type of fruit you have. The important part about machine learning is that we're trying to write one program, a learning algorithm, which is a fancy word or less fancy word for just using statistics and probability rules that can solve many problems. So it's one program with many possible applications. And that way we can pour our energy into building more sophisticated machine learning algorithms, which can be applied across many domains. And that's a very special thing. Machine learning is super old, by the way. As a quick example, so I like games a lot. So is anyone familiar with Deep Blue, IBM's Deep Blue? It's the chess-playing supercomputer. I forget the year, I want to guess. I'd say from the late 90s, right, or the mid-90s. So IBM's Deep Blue, it actually didn't use machine learning at all. It used a huge amount of computational power to search the chess game tree. And basically, if I go here and you go there, and I go here and you go there, and search all the way down and try and guess who's going to win or not. So that's sort of classical AI. It's a search problem. AlphaGo, which DeepMind's, Go, which DeepMind's AlphaGo, just finally achieved parity with the human experts. I think happened a few months ago, and that was a machine learning-based solution. And the reason is that no matter how much horsepower, CPU horsepower you can throw at a game like Go, the game tree is too big. You can't search the space. It's just too big. And so Go, the way AlphaGo worked is it would actually look at a Go position and more or less analyze it visually, sort of like a person would, and try and say, how does this position look to me? And that's powered by machine learning. So one problem with machine learning is that it's incredibly abstract, and until you make it concrete, it's a little hard to understand what people are talking about. So there's a great demo we have, which you can try on your own, but I'll show you in slides right now, called TensorFlow Playground. And this makes it concrete. So to start, imagine that our job was to learn the difference between orange dots and blue dots. It's a very simple problem. We want a Python function that inputs a dot and says it's orange or it's blue. How could we do that? One simple way is we could try and draw a line across the data. We could somehow use this data to figure out, hey, if we drew a line here, then we could say that points to the left of the line are orange and points to the right of the line are blue. And so you can use this line as something called a classifier. It's just like a function in Python that takes a dot, returns whether it's red or blue. And so when we say machine learning, what we really mean is just a procedure that will help us find this line. So we want to learn this line from the data. And it sounds magical, but really what we're trying to do is just plot this line. If you remember, so you can define a line, like a simple equation for a line could be like y equals mx plus b, where I guess m is the slope and b is the y-intercept. So a line has those two parameters. And to learn, you can use the data to adjust the line and move it around until you find one that's a good classifier. And if you open up TensorFlow Playground on your laptop, you can do it after this, you can actually play with something called a neural network live in your browser. It's absolutely beautiful. The authors of this did like a ridiculously good job. And so it's a neural network that you can use live in your browser to classify different data. And a neural network, in a sense, it's drawing a line across the data. But it's just a more sophisticated type of algorithm. So a line might be defined as y equals mx plus b. But if you have a straight line, there's tons of data sets where that's not powerful enough to classify them. For example, like this one, where the blue dots are in the middle, there's no way to take a line and draw it to separate the blue dots from the orange dots. So here's a question for you guys. How would you learn a function, or like how would you draw this? Like what would you have to do to separate the blue dots from the orange dots? You draw a circle, right. So a line, y equals mx plus b, can't draw a circle, but click. In your browser, you can set up a neural network with a bunch of, well, with just a couple actually neurons in the center, and it can actually learn a function as complicated as a circle. And so with a neural net, you can think of the more neurons and the more layers you add, the more complicated of a function it can learn. So here's another function which is more complicated than a circle. So a line can't do it, a circle can't do it, but you can still use a neural network with a few more neurons to do it. So what we're looking at right here, this is a neural net as it might have appeared in like the 1980s. In the center, there's one hidden layer. And so this is like a neural net, and there are many, many, many different types of learning algorithms. So drawing a line across the data, that's a learning algorithm. Using a neural net, that's another one. And there's hundreds more, but they all basically do the same thing. This is before we got to deep learning. And so neural nets have always been extremely powerful, but they're quite slow, and they fell out of favor for many years. This is what's called a deep neural net. So you can see there's many hidden layers. And what's interesting is when you have lots of hidden layers, you can actually input very simple features. And inside the layers, they'll learn properties of them. So basically, the old way of doing machine learning is this. To tell the difference between apples and oranges, you probably wouldn't input the raw pixels into your Python function. You might try and help it out. You'd write some helper functions. You could write something that detects texture, and you could write something that counts colors. And maybe if you had a scale, you could weigh the fruit. So you try and help out the algorithm. You give it some hints. In deep learning, you don't really give the algorithms any hints. You just provide it the raw pixel data. So very simple features that you really don't know what they mean. Like I have no clue what it means for like pixel number 8 to have an RGB value of 50 or whatever. Like it means nothing to me. But when you have a sufficient number of layers, the algorithm can actually figure that out for you. And that's one of the reasons why deep learning has been so successful in different domains. So quickly, I want to show you what kinds of problems you can solve with deep learning. Here I just have like a really high-level schematic of a deep neural network, and it's the same thing you can build in TensorFlow Playground. The first one is image recognition. So the input here could be some pixels, which represent a lion, and the machine learning program could output lion. Here you could have a speech pattern. I'll see you at the restaurant. This is acoustic data. And the same machine learning setup can output, I'll see you at the restaurant. You can also use machine learning in search. So if there was a query like Taco Bell's near me, you could actually use machine learning to rank the relevance of possible documents. Like how likely is the user going to want this particular restaurant or this particular web page based on the query. You can also use deep learning to train a machine translation system. And if you go to TensorFlow.org, I'll get into TensorFlow in a sec, but if you go to TensorFlow.org, you can actually download starter code. It's about a page worth of code where you can literally train end-to-end a system that translates from English to French. So just like a page of code. So deep learning can do the whole thing. So those 4 problems were all things that we've been able to do for a little while and kind of make sense. Like if I show, like if you go to like a classroom where you show a developer those first 4 problems, they're like, oh yeah, like I've seen systems that can do that. But there are some problems that are absolutely blowing out of the water, things we could even hope to do before. So this last one, the input is a picture and the output is a caption for the picture. So you can use machine learning to automatically generate a sentence that describes an image. And that's something that's so far beyond, like I could imagine if you gave me like $1 million in like 10 years, I'll write you a Python program that can recognize images. Or I can use my knowledge of machine learning to eventually build you like an okay speech recognizer. Like those are things I believe I could do. It would not be fun, I'm not great at it, but I could do it. But until deep learning, I don't think there was any developer like in the world who could have said, yeah, give me a picture and I'll generate you a caption. And not to plug Microsoft, but they actually have a really great demo of this. I forget the name of their machine learning package, but if you search for like Microsoft machine learning image caption or demo, they actually have it live on their website. But TensorFlow is way better. Yeah. Anyway, last slide and I'll get into TensorFlow. So deep learning is basically everywhere at Google, and pretty much there's a whole like giant box of different like machine learning systems that are open source, and Google has their equivalent, machine learning boxes, which are basically just internal versions of the external stuff. But pretty much everything is being migrated to TensorFlow. All right, so that's a lot on what machine learning is, really quickly what deep learning is. The problem with these topics is it's a little bit much to wedge into like a 30-minute talk. We really would need a couple hours. So the TLDR is machine learning it's just the study of algorithms that learn from data. You can replace, machine learning is a great buzzword and so is deep learning. Replace machine with programming and learning with statistics. So machine learning is just programming statistics. And the beauty of a lot of toolkits that we have is I am not a statistician, but the toolkits actually take care of a lot of the stats for you, which makes it accessible. So now let's talk about TensorFlow. So what is TensorFlow? It's a cool sounding name, but first of all, what is a tensor and what does it mean for tensors to flow? Right? So I didn't know what a tensor was until I learned about TensorFlow. So who happens to know what a tensor is, who's not a physicist? Yes, so a tensor is a multi-dimensional matrix, or a multi-dimensional array. Someone who's a physicist will probably have a different definition that's a little bit more sophisticated. But in TensorFlow, by a tensor, we just mean a multi-dimensional array. So that still sounds a little complicated. What the hell is a multi-dimensional array? So here's some examples of tensors. So a scalar is a tensor. Like you could have a variable s equals 7 in Python. That's a tensor. You could have a vector, v equals 1, 2, 3, or a list. That's a tensor. Or a matrix, a two-dimensional array. Or you can have a cube of numbers. Those are all tensors. So a tensor is just a generic data type. It's super, super generic. It's a number or a list or an array. All right, so what's flow? Well, in TensorFlow, flow is a graph of operations that you do on tensors, which also sounds incredibly abstract and incredibly complicated and doesn't really make any sense. So I spent a long time looking at like, the hell does it mean for tensors to flow? And I puzzled over it. And I really had trouble understanding it until I watched a really kick-ass lecture from Stanford, which was an intro to TensorFlow. And they were the first people that I think really explained it effectively. So let me walk you through an example that I borrowed from their lecture notes. So here's how you might use TensorFlow in Python to multiply two numbers. First thing we can do is we can import TensorFlow. Now I'm going to create a constant. I'm saying a equals 2. On the left you see the Python, and on the right you see the graph. So this is a graph we're building up. So now on the graph we have one constant, 2.0. Now I'm going to make another constant, and I'll call it b, and I'll say b is 3. Now we have two nodes on the graph. Now to multiply them, I'm going to create a multiply operation. And I'm saying c should multiply a and b. So now we have a multiply node on the graph. So by flowing, what we really mean is the work being done on that graph. And by tensors, we mean we're doing work on arrays. And then if we want to get the output, we can ask the graph to evaluate the value of c. And then the graph will go out and do some work, and it will come back and say, hey guys, 2 times 3 is 6. So this is the super low-level way of writing TensorFlow. So under the hood, it's a little bit like NumPy. It's just a general-purpose library to do math with tensors. So super, super low level. This is the assembly language way of writing TensorFlow. But what's really special about TensorFlow, and you can do this. So if you're a machine learning researcher, or you're an engineer, or you're a physicist, or whatever, and you have some really complicated problem, you can write nitty-gritty TensorFlow code. But there are also APIs with TensorFlow, one-liner APIs, where you can say, I want a classifier, and it's going to be based on a deep neural network with so many hidden layers and so many nodes. And so just one liner, and behind the scenes, that line will create thousands of lines of low-level TensorFlow code, and it's ready for you to use. I'm going to talk a little bit about why do we need a library like this? So there are tons and tons of machine learning libraries. And I can tell you that within I think a month or two of TensorFlow being released, it was by far the most popular one on GitHub. By far. It just crushed it. And I joined the team after that. I had nothing to do with that at all. I wish I did, but it crushed it. So why was this such a big deal? Like, it's just a low-level library like NumPy for doing math with tensors. So like, why is that a big deal, and why do we care? So the problem is, when you want to train a machine learning model, maybe you're teaching it to recognize cats and dogs. The way you do that is you might need lots of training data, tens of thousands or even millions of images of cats and dogs. And to train a statistical model like that takes a huge amount of number crunching. It could take years on a single laptop. So instead, you want to use a data center. And you want to use many laptops or many CPUs and many GPUs. But the problem is that writing code that can take an algorithm and then efficiently send it out onto a data center and all these GPUs is extremely hard. And it's a very different skill set. So there are system engineers who really mastered this problem, right? These are guys and girls, they focus on low-level optimization, and they understand distributed computing and all this, and numerical optimization. That's a whole discipline. And then there are people that are doing machine learning research, and these are often completely different sets of people. And so the goal is, we want a way for somebody to write a machine learning algorithm at a high level, and then take advantage of all these years of engineering work to execute it efficiently, either on one machine, or one GPU, or multiple GPUs, or a data center, or a cluster, or whatever. And this is actually a really common problem in computer science, right? Who's familiar? So I write a lot of Python and some Java, but who's familiar with a library called NumPy? I wonder, here's a question that I don't know. Is somebody who knows Python and Java, does Java have any libraries like NumPy, or does it not need them because it's fast enough? Am I not? Like, so basically, here's the trick in Python. So why do we like a language like Python? And to some extent, a language like Java? Well, the same thing is true. So before Java and Python, we'd often write code in C, or maybe C++, which is great, right? Because you can write really performant code in either of those languages. And you can do all sorts of low-level optimization. And it runs really fast. But the problem is, honestly, I don't really care how fast my code runs. Because my time, I have a limited amount of time. And as developers, we could be using our time for something more important. So we want to write code in high-level languages, but still have them execute quickly. So Python is particularly slow. I would imagine, if I had to guess, it's maybe 10 times slower than Java, depending on the problem you're working on. But Python is hugely popular with people who do something called scientific computation. Like physicists and people doing climate modeling, they love Python. And that's really a hard problem to solve. It's a lot of compute work. So why do they like Python? Well, there's libraries for Python, like NumPy, that let you write high-level Python code and actually behind the scenes execute it in C really efficiently. So the developers who've written NumPy have made it possible for other engineers to write high-level code and still benefit from some of the performance enhancements. And TensorFlow is a very similar idea. It's a lot like NumPy, except it goes a couple steps further. It adds GPU support, and it adds distributed support. And it also adds tons of super optimized code for doing machine learning. And so that's why it took off to the extent that it did. The other important thing about TensorFlow is it runs pretty much anywhere. So there are two front ends. Python is the most popular one. You can also use C++ for the high-level APIs. I don't believe there's a Java front end yet. If you're new to Python, it's not so bad. It's actually a hell of a lot easier than Java. So if you can write Android code, you absolutely can write TensorFlow code. It's massively easier. So typically you write your code, you write your graph, or you use the high-level libraries in Python. When you hit execute, they go to this ultra-optimized C++ backend, which handles talking to GPUs and talking to clusters and does the actual work. And when that work is done, it brings it back and delivers it to you. And the cool thing about TensorFlow is it actually can run also on Android and iOS. So it's not quite universal, but it's close to universal. It runs almost anywhere. So I have a lot more slides that I don't want to go into right now, but we can. I can walk you through actually solving a machine learning problem in TensorFlow if we have time. But there's two things I'd like to open up. One, I want to leave lots of time for questions. And two, where my team is working on a content bundle for you guys. We didn't quite make this deadline, but most likely, I don't want to promise a date, but I will make sure it gets sent out. And the idea for the content bundle It's much more code intensive than this. Right now it has something like 90 slides you guys can mix and match. And it